I want to understand reinforcement learning, the kind of artificial intelligence associated with real-world virtual robots. The way I understand things is by talking about them as if I do understand them, so let's go! Supervised and unsupervised are two kinds of machine learning algorithm. A supervised algorithm is given data which is labeled. The algorithm learns to guess the label given just the data. One example is a convolutional neural network which guesses if a picture is of a cat or a dog. There's a correct answer any human or squid should know. Another example is a recurrent neural network text generator which continuously guesses the next word, assuming it was written by Stephen King. There's only one human or squid who could answer that correctly every time, Stephen King. An unsupervised algorithm is given data which is not labeled. The algorithm labels the data on its own. One example is k-means clustering. When I supply data and ask for 4 labels, k-means clustering can show a reasonable way to divide the data into fourths. This data is obviously very easy to label like this, so here's data we might want a computer to look at. If I don't like the computer's labels, I can tell k-means clustering to do it again. The algorithm begins with randomness, so it might be different every time. Beginning with randomness also describes reinforcement learning, and my way of learning about reinforcement learning. I found one tutorial online, barely understood a word of it, then found a second tutorial online of which I understood 2 or 3 words because I'd read the first tutorial. Then I went back to the first tutorial and understood a few more words this time, and moved on to yet a third tutorial, and so on, until I eventually got my own code working. That's how programming works, squidlings, write that down. But it's also how reinforcement learning works, kinda. Let's look at the hello world of reinforcement learning. The Python package OpenAI Gym provides a bunch of robots to play with. The simplest of these robots is an inverted pendulum in 2D space. There's a pole pointing up, always about to fall over, and we want the robot to keep the pole upright by accelerating left or right. Accelerating left or right are the only options the robot's got. It can't even stand still, it must keep moving. We teach the robot to move successfully by scoring it. At every moment, we announce a reward, a number based on whether or not the robot is doing what we want it to do. Here, the robot gets a reward based on how high the inverted pendulum is reaching. Whenever the robot is asked to decide left or right, it considers its current observations and predicts what its next reward would be given either choice. If it thinks the reward would be better accelerating left, it accelerates left. If it thinks the reward would be better accelerating right, it accelerates right. So this robot is controlled by a neural network which turns the image of its predicament into expectations for its next reward. Much like training a supervised machine learning algorithm, we reinforce this robot's neural network by comparing its expected rewards to actual rewards. See, the robot has a memory of all its previous observations, its actions, its next observations right after those actions, and the rewards it got from all that. So we can train the robot by picking out a bunch of these memories at random and comparing 2 numbers which are somewhat difficult to describe. It's as if the robot looks at new observations and thinks, whoa, I've seen something like this before, and I did that. How did it turn out? But wait, when did the robot get all these memories? We actually start by making the robot choose actions at random. This provides a lot of memories for data. We call this exploration, which declines slowly over time. Anyway, these 2 numbers we're comparing during training, this first number, okay, geez, let me dig in here. You get the robot's opinion on what each action's next reward would be based on the memory of an observation. Then you pick out the reward of the action it actually remembers choosing at the time. This second number, oh boy, okay. The easy part is the reward the robot remembers getting on that move. But you're going to add something to it representing the potential for more rewards in the following moves. You get the robot's opinion on what each action's next reward would be based on the memory of the next observation. Then you pick out the highest reward there. Multiply this sum by some gamma to de-emphasize forward thinking. If we do enough training on this inverted pendulum robot, it's not too bad at staying inverted. Okay, I think that's the hard part, but I think I got it right. Let's try it out on our own robots. I used PyBullet instead of OpenAI Gym to make a simple version of the predator/prey game I've been proposing. So I'm training 2 robots at once. At every moment, these 2 orbs each have a few observations. They have a picture of themselves from above, like they're starring in an arcade game. They know how fast they're moving in the X direction and the Y direction, and they know their distance from the other orb. I'm rewarding the orbs for getting closer together. I decided these orbs are both moving at constant velocity. At each moment, they decide to either keep moving like that, or tilt their velocities yaw 60 degrees to the left. Gosh, this has gotten me back into trigonometry. First, we put the orbs through training. The orbs experience the scenario for a few frames, and then the scenario restarts with the orbs in random positions moving in random directions. I do this a whole bunch of times, so the orbs have training in a whole bunch of different scenarios. Sometimes picking decisions themselves, but mostly choosing at random to explore. Now, let's test the orbs by turning their exploration all the way down. Those orbs look like friends, huh? I trained the orbs again, but this time I rewarded them for getting farther apart. Now they're not friends anymore. Aww. I made another one of these where each orb has a first-person camera. Now they need to choose between 3 actions, continuing as they are, rotating their movement 60 degrees, or rotating their vision 60 degrees. These orbs seem like friends again, and they're really trying. There's a lot of work to do before this looks like the predator/prey scenario I've described. But thinking about thinking is all I do here at Thinkster, so I'll keep it up. I might introduce recurrent neural networks next, or maybe I'll try to figure out continuous reinforcement instead of this discrete reinforcement. Apparently, that's called the actor-critic method, which sounds quite a bit like a generative adversarial network, doesn't it? Bye-bye. By the way, I've got a Patreon at patreon.com/thinkster. I want to thank all these squidlings and elder squids. Thanks.